Last time, we drew a line to predict a number, a price. But so many real questions are not how much. They are yes or no. Is this email spam? Will this student pass? For those, we need a small twist on the line. Here is our data. Each dot is a student. Along the bottom, how many hours they studied. The answer is only one of two things. Down here, the ones who failed, marked 0. Up here, the ones who passed, marked 1. Your first thought might be, just use the same straight line. And you can draw one. But watch what happens at the edges. For a lot of hours, the line shoots above 1. For very few hours, it dips below 0. But a chance cannot be more than 100%, and it cannot be negative. The straight line gives impossible answers. We need to gently fence it in. Here is the fix, and it is beautiful. We take that same straight score, then bend it through an S-shaped curve called the sigmoid. The sigmoid has a magic property. No matter how big or small the score, the output is squeezed to live strictly between 0 and 1. The far left flattens just above 0, the far right flattens just below 1, and it rises smoothly in the middle. Now every output is a real, honest probability. Reading it is easy. Take a student who studied 6 hours. Go up to the curve, then across. The height is the answer, about 0.8. The model is saying there is an 80% chance this student passes. Not a flat yes, a calibrated confidence. So here is the whole model in one line. First, the same linear score we already know. Hours times a weight plus a starting value. This score is just raw evidence, and it can be any number. Then we wrap that score in the sigmoid. That turns the raw evidence into P, a probability between 0 and 1. Linear evidence in, clean probability out. That is logistic regression. To make an actual decision, we draw one more line. A threshold, usually right at 1/2. Above it, we predict pass. Below it, we predict fail. The spot where the curve crosses the threshold is the decision boundary. And here is a subtle, powerful idea. That threshold is a choice, not a law. If missing a real case is dangerous, like a disease test, we lower the threshold to catch more. If false alarms are costly, we raise it. Same model, different policy. One more question. How do we train it? We need a way to score how wrong a probability is. And the rule is strict. Being a little unsure is forgiven, but being confidently wrong is punished hard. Picture a student who clearly passed, but the model swore they would fail, with 95% confidence. That mistake earns a giant penalty. This is called cross-entropy, and it makes the model care most about its loud, certain errors. Last warning, and it matters a lot. Once you can classify, do not trust accuracy alone. Imagine 10 spam emails hiding among 990 normal ones. A lazy model that just shouts never spam is 99% accurate and completely useless. It catches nothing. So we also ask, when it flags spam, is it right? And does it find the real spam? Those are precision and recall, and they keep us honest. So logistic regression keeps the simple line, then adds a sigmoid to turn evidence into probability, and a threshold to turn probability into a decision. It is the honest baseline for every yes or no question. But a line, straight or curved, can only split the world one way. Next, we meet a model that carves it up by asking a series of simple questions. Decision trees.